Hello everyone. Today we will discuss about the problem 6.2. It's about border rule. The border rule is commonly used for making collective choices. Let's there be n individuals and suppose X contains a finite number of alternatives. Individual I assigns a border count Bi of X to every alternative X, where Bi of X is the number of alternative in X, to which X is preferred by agent I. Alternatives are ranked according to their total border count as follows, like this way. So the question is, show that border rule satisfies U, W, V, and D. The second question is, show that it does not satisfy II, which is independence of irrelevant alternatives. So first, we will solve the question number 1. Let's see. Border rule satisfies U, W, V, and D. So first of all, let's consider a society with 4 individuals, n equal P1, P2, P3, and P4. And 4 alternatives are X, Y, Z, and A. Let's assume that P1 is a dictator and individual preference and social choice are like following. So we made this table. We can see their individual preferences, and this is ranked by 1, 2, 3, and 4. So let's calculate the social choice. For X, 4 plus 3 plus 4 plus 4. Okay, how we calculate this? We can discuss here. For X, we can see that X is ranked here 4. So 4, here X is ranked 3, here 4, and here 4. So by us adding these values, we get 15. For Y, rank is 3, 3. Here rank is 2, here 2, and 3. Like this, 3 plus 2 plus 2 plus 3. In the same way, we will calculate for Z and we'll calculate for A, and then we will get this value. Now, we have to count the Borda count. Here we can see that X is preferred to Y, which is equal 4. But how? Let's see. Here we can see that X is preferred to Y, 1. Here we can see the same thing, 2. Here we can see the same thing, 3. And here, the same, X is preferred to Y. So we will get 4. In the same way, if we look this table, we can find the value 3. And same for all of these calculations. So if we add them, 3, 4 plus 3 plus 3, then we'll get 11. Then we'll calculate B of Y, B of Z, B of A. We'll get all of this calculation. It's a very simple way. So now Let's see. The social choice is X is preferred to Y is preferred to Z, and Z is preferred to A. So the social choice is this, and since the preference of P1, we can see preference of P1 is the same. It's like the social choice. So we can say that P1 is a dictator. Then WP. WP means weak Pareto principle. So for P1, what we'll see? X is preferred to Y. Yes. For P2, X is preferred to Y. Yes. X is preferred to Y for P2. For P3, X is preferred to A and A is preferred to Y. So we can say that X is preferred to Y, which is said here. And for P4, X is preferred to Y. We can see that X is preferred to A also. So the social choice PS, X is preferred to Y. So it satisfies the weak Pareto principle. Let's see. We have P1 here, P1, Z preferred to A, Z preferred to A. And for P4, here P4, A is preferred to Z, which implies that Borda rule satisfies all the possible pair. Hence, thus it satisfies the axiom of universal domain. Yes, we can see that it satisfies universal domain, which is denoted by U. So, we discussed about the solving procedure of question A. Now, we should discuss about the problem. Show that it does not satisfy IIA. Okay. So, here we have table 1 and table 2. There is a slight modification here. X and Z and X. Here X and Z. A slight change. But we are keeping the preference order Y preferred to X intact. Here we can see Y preferred to X, and here we can see Y preferred to X. We kept this thing intact. So let's count the Borda count for table 1. If we count this, like X is preferred to Z, here X is preferred to Z. Number of vote is 5. X is preferred to Z. Here number of voters is 4. We don't see any X preferred to Z here and here. So 4 plus 5 plus 4 equal 9. X preferred to Y. Here X preferred to Y equal 5. Nothing is here. So you get 5. If we sum all of this, B of X, we got 14. In the same way, here B of Y, we get 18. And in the same way, we get 16, B of Z. So what we can see, the value of B of y, which is highest. Then we get B of z, which is 16. Then 14, which is B of x. So we can see that the winner of border rule y, then z, then x. We can say that y is preferred to z and z is preferred to x. For table 2, if we count the Borda count in the same way, x is preferred to z. Here we get 5 vote. X is preferred to z, 4 vote. And x is preferred to z. We get 3 vote. 5 plus 4 plus 3 equal to f. X is preferred to y. 5 vote and 4 vote. X is preferred to y. Here x is preferred to y. So by adding 4 plus 5 plus 4 equal to 9. So if we calculate b of x, we get 21. If we calculate b of y in the same procedure, we get 18. And if we calculate b of z, which is equal 11. So what we can see, there is a difference that the winner of the border rule is x preferred to y, y preferred to z. So we can say that border count does not satisfy II, independence of irrelevant alternatives, since non-winner x turned into winner, while no one reversed their alternative preference of x versus original winner y. By IIA, if y is preferred to x out of the choice set x and y, then introducing a third alternatives, which is z, thus expanding the choice set x, y, and z, must not make x preferable to y. So we can see that border rule does not satisfy IIA. And yes, we have solved the question B and we discussed it. So thank you everyone for watching this video.